Well, first of all, I'd like to thank Xin for inviting me to give a talk here. So this is my first time to visit the Netherlands. It's wonderful, but I know Michelle for many years. So it was like, what, 2008, right? When I was a PhD student, and Michelle was a visiting professor at Stanford, and we had some small project back then, right?
We can never keep that.
Yeah, it was find another opportunity to cooperate. But anyway, the talk that I'm going to present today is about queuing, but this is for some people who know me well, like Jing, Galit, and maybe Jingwei and Dongyuan. This work actually started many years ago, and we never got a chance to finish the manuscript, in academia, right? So many reasons. But anyway, we finally got a chance to finish the project recently. And as I said, this joint work with Jeff Hong, Ji Heng, and Wei Huang from Nanjing University. So when we started the project, Jeff, me, and Ji Heng, we were sort of, well, at least for me and Ji Heng, we were both assistant professors back then, but now Ji Heng is our department head, so so you see the time flies, right? Anyway, okay. So this is a queuing talk. So basically, our focus is to try to build a new, quote unquote, new continuous time model for rivals, for the purpose of doing staffing, a very traditional topic in queuing theory. Okay. And of course, one could argue that many staffing formulas conceptually has this structure of you want to set the staffing level in such a way that you meet the expected demand first, and then on top of that, you have some buffer to counterfact the stochastic fluctuation in the demand. Okay. So we all know that if you have stationary arrivals to the system, then the most standard model will be a stationary Poisson process, and if we consider n as the number of arrivals or arrival count within a unit time period, and set lambda to be the arrival rate, then when you have sort of a large arrival rate in the heavy traffic, then the variance of this number of arrivals will be sort of like will be scaled as lambda itself, because obviously because it's n under this Poisson process model, the n will have a Poisson distribution, and with the mean of lambda, and when lambda is large, this n will be approximately having the same distribution as a normal distribution with the mean lambda and the variance lambda as well. And this is sort of like conceptually is the intuition behind why we will have square root staffing, okay? Because you see, if you compare the formula that I showed you on the last slide, if you want to meet some kind of service objective, then you want to fulfill the demand from the average arrival, and then you adjust it up by some buffer that is sort of proportional to the standard deviation of the arrival, the standard deviation of the demand, which is in this case will be square root of lambda. Okay. But of course, in reality, this could be the kind of pictures that many papers will show you, right? In reality, if you have hospitals or other kind of service systems, the arrival process obviously has the time of day event, time varying. And again, a typical model, a standard model to in this context will be generalized from the stationary Poisson process to a non-stationary Poisson process, which is also sometimes called inhomogeneous or non-homogeneous Poisson process. Okay. Then there's back to the question that whether this assumption, this Poisson assumption, whether either you mean by Poisson assumption either you mean the stationary Poisson or non-homogeneous Poisson, whether there will be a valid assumption, right? So of course this is a sort of a study, decades ago, and there are different answers, right? Based on various statistical tests, okay? And of course, these different answers, some say yes, some say no. Of course, they get these different answers from different data sets, but actually, the reason why you get different answers is not because of the data sets per se, but because of how you look at the data, how you perform the sort of a statistical test. Okay. So first of all, for example, again, for now, I'm going to assume that sort of like inhomogeneous Poisson, because this is the more general case. So if you have a inhomogeneous Poisson process, then this is a very basic fact that you can perform a time change by inverting the integrated arrival rate. Then you can transform a inhomogeneous Poisson process back to a unit, sort of a standard Poisson process with a unit arrival rate. And based on this fact, you can do several different hypothesis tests. Okay. So first of all, for example, you could test, if you have a standard Poisson process, then stationary, then of course the interval time will have exponential distribution. Right, the very basic facts. That would be sort of the first test you could do. And on the other hand, another test you could do is you can test against the distribution of the arrival count. Right. In addition, instead of testing the distribution of the interval times, you can test the number of arrivals within a given time period. So for the first kind of course, this is all not new stuff, very sort of very standard stuff. So you can actually try this on various data sets, and then you can see that after the time change, right? So you start with the inhomogeneous Poisson process, you have a data set, then you run this very simple exercise, and then look at the interval times after time change, then you see that it's a very much almost perfect fit to exponential distribution, right? So now you have a sort of a rigorous statistical test that tells you that Poisson distribution or inhomogeneous Poisson process is a valid model for the arrivals. All right, but of course, then you can look at a different way, right? So if you have a inhomogeneous Poisson process, then your arrival count will have a Poisson distribution. So this is also something that you could test very easily. You can have a lot of different tests. On the first row, you see the arrival count within the 5 minutes, right? You have a different days, and then you look at number of arrivals within the same 5 minutes on different days. You put them together, you have a distribution. Then look very much like a Poisson distribution. So that means you can pass the test. But then you increase the length of the interval, right, from 5 minutes to 1 hour or half an hour or even longer. Then you do the same test, and you don't even do the rigorous statistical test. You look at a picture, then you see that it obviously is not Poisson distribution. Okay. So yeah, this is a test they could do. Very standard Fisher test. Just test the Poisson distribution based on the property that the mean and the variance of a Poisson distribution should be equal, right? If they don't equal, if this ratio is greater than 1 significantly, then you fail test. So now, yeah. Yeah.
The test that you did before was within a day, a specific day, right?
Mm-hmm.
And the second one is across days.
Yeah, across days. Yeah.
Why do you expect it to be the same parameter?
I'm sorry. Why do you expect it to?
Are you expecting it necessarily to be the same parameter?
You mean lambda?
Mm-hmm.
Right. If obviously, if for different days, you can restrict. If you sort of like if you want to take into account the say a day of the week, then of course there's some variation on Monday, Tuesday, and Friday. But you could say just take out Monday, right? For different Mondays, just assume that for that you could assume that within that same table. Yeah, I agree.
It's a different when you're estimating within 6 minutes, and then you are trying to infer that it's the same within 1 hour.
Yeah, I agree. I'm just saying that it could maybe not 1 hour, maybe say 10 minutes or 20 minutes will be considered as a relatively constant. Yeah, I was thinking that this is a kind of like at least a model that people use quite often, right? So across different days, you may want to use the same rate to build a model. So obviously you cannot have say 365 days. You have every day you have a different rate. So from modeling point of view, that's too complicated, right? So yeah. Well, anyway. Okay. All right. So my whole point is, I mean, if you do the test, then basically the same test, you start with a very short time period, then the test actually passes, but as you increase the length of the interval, it actually gradually fails. Right? So now intuition is actually quite simple. You can think of this as all these small, very short time periods. So essentially, there might be some very small autocorrelation between different time intervals. But if this time interval is very short, say 1 minute or 2 minutes, the autocorrelation is so small that it's very hard to be detected through hypothesis testing. However, if you aggregate all these small intervals across, right, then this very, very small autocorrelations will add up and will contribute to the relatively large variance overall. So that will make the Poisson distribution fail over a relatively longer period of time. Okay. So now you basically have the issue of the modeling issue, and kind of what kind of model that you want to choose. Obviously, we don't have an absolutely correct model, but the idea is if you consider a very short time period, right? So within minutes, within seconds, then obviously, clearly you could have a Poisson kind of behavior, right? Like interval times you saw earlier, you have a very almost perfect fit to the exponential distribution, right? So within a very short time period, you could use a Poisson kind of model. But over time, if you have a sort of over the day, then the kind of a time variant pattern will kick in. In that case, you don't want to have a stationary model. You want to have a model that built in sort of a time varying or predictable pattern to describe the average rate of arrivals. But in the middle, right, in the between, so like a minutes, in 5 minutes or up to 30 minutes, give or take. Then you saw earlier that the kind of test on the Poisson distribution, the variance actually significantly higher than the mean. So in that case, this is well documented. It's called a over dispersion phenomena, and that's actually will tell you that the Poisson distribution actually is not a good model for that kind of time scale. Okay. Yeah.
For the macroscopic time scale,
Yeah.
a time varying Poisson process actually works well.
No. I mean, I'm saying. I'm more like saying that you could have you should focus more on building a model to capture the time variant pattern. Now I'm saying that the inhomogeneous Poisson process model actually works on that macro time scale. I see.
The first order thing is the time variant.
Yeah, the first order thing is time varying, right? Yeah. Right. Okay. So this is a picture that I think many people are aware of, or similar pictures. So basically, over a day, then you could have the mean of the arrivals will have a strong time of day effect, and then if you look at the variance, it's also quite significant. Significantly higher than what the Poisson distribution may predict. Right. So here you see that the blue band is the kind of like one standard deviation predicted by Poisson distribution. But what I really observe in the data set, here is a call center from New York City, but it actually applies to many other data sets. Then the the red band is what you already observed, the one standard deviation from the mean, right? So it's quite significant. So now the project that we've been working on is again, this over dispersion fact is well documented, but we want to ask the following three questions. First of all, is there a sort of very basic law that governs the observed over dispersion? Right? So I'll explain what I mean by that. And secondly, is it possible to develop a simple random model that can capture this over dispersed phenomena? And third is, given this model, then how would you derive a Stanford formula, right? Okay, so this is where the Taylor comes from. It turns out that there's a law called Taylor's law, very simple. And so before I get into that, I'll just give you some notation. N is the number of arrivals within one time unit, and we call it as over dispersed if the coefficient of dispersion, which is the ratio of the variance to the mean, is greater than 1. Okay, and then the staffing rule again is basically have this structure of the base staffing level will be essentially the expected value of this arrival count within 1 unit of time, and then you add to some proportion, some part proportional to the standard deviation of this arrival count. And beta actually controls the target service quality. Here you have two very basic scheme regarding the staffing rules. If you have this is something that we saw earlier. If you have a Poisson process model with the rate lambda, then the staffing rule will be lambda and plus a square root of lambda proportional to square root of lambda. And then if you have a so-called double stochastic Poisson process model with a random arrival rate, which is a lambda multiplied by a random variable. So this is a random variable without time evolution, so there's no dynamics. But if you just consider it as a random variable, g, then the safety staffing part will be in the order of lambda when lambda is large. Okay. Now you see that between these two streams, obviously the key is what is the variance of your arrivals relative to the mean when lambda is large. So this is something that you want to basically that kind of relationship differentiates these two different staffing rules. So now you want to basically look at, okay, I want to do some kind of a heavy traffic analysis. I want to send the lambda goes to infinity, but the key here is I want to understand what is the relationship when lambda goes to infinity. What is the relationship between the variance of the arrival count within one time period of time relative to the mean? Okay, so here you are looking at sort of like the same picture that I showed you earlier. So this black dashed line is the mean of the arrivals within different time periods of the day, but you take a logarithm. Okay, and then the red line is the variance of arrival count. The corresponding variance of arrival count also take a logarithm, right? So now if you look at these two curves, they are very much aligned with each other. So very naturally you want to ask, is there a relationship between these two curves? So basically you see like can think of this every 10 minutes you have one number, right? You have the two series, and then you want to see, okay, what is the relationship? And then very simple, you can just run a linear regression, okay? And actually matches linear regression quite well. Have a very R square is very close to 1, okay? Very heuristic analysis. Okay, there's linear relationship. So that basically means that the variance of the number of arrivals within, say, a delta period of time, and the mean of the number of arrivals within the same period of time, and there's this on the logarithm scale, there's a linear relationship. So this suggests obviously the variance will be some kind of power of the expectation, right? So, okay, of course, so this is something that. So later we found out that this is actually called Taylor's law, and was discovered by Taylor in a completely different area back in 1960s in ecology in UK. Okay, when he studied the population of different species, the population of some species within in different geometric locations, he identified this empirical law, and it turned out that. Apparently there's this book called Taylor's Power Law, and basically documented the same phenomena in various disciplines, from finance, geology, sociology, economics, computer science, even, right? So written by Taylor, but this is not the same Taylor, but actually his son. So, so I said, I told my wife that if work hard enough, you get something that your kid can live on. So anyway, right. So Okay, so obviously, again, as I said, this empirical law we did not actually discover this empirical law first. This is even within the queuing literature. It was discovered, found, back in 2009. Maman, who was she? I guess she was a master student, I guess, right? But we didn't know this, but later on, of course, we found out that she actually found this empirical law in the context of a call center. Okay, and the model that people use to capture this so-called Taylor's law was a doubly stochastic Poisson process with random arrival rate and something like this, right? So we have a random arrival rate. And this random arrival rate is a random variable. Again, there's no dynamics. This is not a sort of a continuous time model, right? So rate is treated as a random variable. And then many people build on this model to derive corresponding stacking formulas. And most recently on Hu Yuan, Jing, and Carrie. Oh, I'm sorry. Since when? Since like 2 seconds. Okay, good. All right. Good. Okay. All right, so building on this model, they derive the stacking formulas in various contexts. There's some contexts on some examples in healthcare, some in telephone call centers. Okay, so we want to actually the tuition is, given this model, so they derive this formula look like this, and the tuition very clear. So just like what you saw repeatedly earlier, so you have base stacking level, then plus some safety level that is proportional to the standard deviation of the demand, loosely speaking. And here the standard deviation of demand is in the order of that lambda to the power of alpha thing. So here what we want to do is we want to develop a continuous time model, right? So instead of having this random variable as a arrival rate, we want to have a stochastic process to build the model so that you can simulate sort of a smoothly plug in our model, this continuous time model, into the traditional heavy traffic queue analysis. Right? This is what we want to do. So this is the model that we propose. So again, still a doubly stochastic Poisson process, but the arrival rate here I want to make clear. So here the model that we develop is still a stationary model. So later I'm going to talk about how to generalize this stationary model to capture time varying effect. Okay, this is still stationary model. The arrival rate, that's called xt. This is a stochastic process. Instead of random variable independent of t, we have a stochastic process. And here the stochastic process is we make this assumption. This stochastic process satisfies this SDE, stochastic differential equation. And if you have some background in financial engineering, you may recognize that this is a process called a CIR model or Federal diffusion if you come from a more mathematical background. But the key difference here is here. For the so-called CIR model used in finance to model interest rate, in their SDE, there's no this part. There's no this part. So lambda to the alpha is something that we introduced. Okay. So for the standard CIR model, there's no lambda to the alpha part here. So this model, there's some good properties about this process. The most important that is this stochastic differential current always takes some positive values. Okay. So of course, the motivation was, if you want to model interest rate, you want to have a stochastic process of state positive. But of course, now we know that interest could be negative effectively. So, right. So we call it generalized CIR process just because of this factor. Okay, so meaning that if you set the alpha to be equals 1, then you reduce this SDE back to the standard CR process. Now, why do we want to have that lambda to the alpha part? Well, remember that we want to have a model that basically says, match the Taylor's law, match that empirical observation, where the variance of the rival count has a power law relationship with the mean, right? And the power of that power law will be something related to alpha, right? So here is the intuition. So for this CR model, it is a stationary model, meaning that it has a stationary distribution, a limiting distribution. So that roughly means that when in stationarity, this lambda t roughly have the order of lambda. So this is a long-run equilibrium. So you loosely speaking, consider xt to be equal to lambda, loosely speaking. And then you have this diffusion term that has the square root of lambda to the alpha part. And if you consider xt as loosely speaking as has a magnitude of lambda, then this term will have roughly speaking has the order of lambda to the power of alpha plus 1 over 2. Okay, and then the contribution to the variance of the AT will be the Poisson process conditional on xt. Will be the variance to the contribution to the variance will be of order of lambda to the power of alpha plus 1. Okay. So now you actually, because this CR model, even though at first it may look like complicated, but actually quite tractable analytically, you can derive various formulas. For example, you can derive its station distribution and derive and then calculate the variance of this rival account under the station distribution in closed form, and then you can basically verify that under this model, then the coefficient of variation, which is the variance divided by the mean, loosely speaking, we will have this kind of formula. Then you can actually have this, coefficient of variation roughly in the order of the mean to the power of alpha. So this model actually can capture that Taylor's law, the empirical observation. Okay. And then you can also derive some, this is a kind of like a theorem that the centerpiece of this presentation. Remember that we want to so eventually after building up this arrival process, we want to perform some heavy traffic analysis. So here is the first step for that heavy traffic analysis. We want to derive a sort of scale up the rival process, this new rival process. We want to scale it and then look at what is the symptotic distribution of this scaled rival process as lambda goes to infinity. So now, when you do the scaling, of course, you want to first center the rival process by its average. So average, the mean of average, the average of AT obviously is lambda t. So that part is simple. But when you scale it, multiply by a scale factor, then you want to scale it by, of course, you want to scale it by 1 over the square root of AT. And then this guy, the variance of AT when lambda is large is actually in the order of lambda to the power of alpha plus 1. So you want to basically scale. So the scaling parameter, the scaling scheme is not the traditional square root kind of scaling. It's actually scaled by this lambda to the power of something related to alpha. And then you can show that the scaled route process will convert to a non-trivial limit. And this limit is quite interesting. It actually consists of 2 parts. The first part is an integrated OU process. The U here, this is a Ernst-Uhlenbeck process driven by the same Brownian motion that defines the CR model, defined in the arrival rate. That's the same Brownian motion. And then the second part in the limit is another Brownian motion, the B tilde. So that Brownian motion is independent of this one, and that Brownian motion actually comes from the conditional Poisson part. Right? If you think about it, if you have a standard Poisson process with a constant arrival rate, then you do scaling, then you can show that Poisson process will convert to a Brownian motion, right? So that B tilde actually comes from the Poisson part. This Brownian motion comes from the intensity, the 2 independent Brownian motions. Here, this Brownian motion actually also, it takes effect only when alpha equals 0. So that means when alpha is greater than 1, so we have this non-trivial Taylor's law kind of effect. That means when alpha is positive, this part doesn't appear in the limit. So that actually suggests that when you have a Taylor's law, that kind of empirical observation in the heavy traffic limit, the randomness is actually governed by the stochastic intensity, not by the conditional Poisson part. Okay, but when alpha equals 0, so these two, the conditional Poisson distribution and the intensity, this kind of two sources of randomness that define the double stochastic, actually they have, loosely speaking, they have the same kind of magnitude of fluctuation. So they both contribute to this limit. Okay, so this, this analytical result is quite interesting because it involves, if you think about it, it involves several different stochastic processes quite commonly used in practice. You have a Brownian motion, you have a OU process, CR model, and even have a Poisson part, right? So, I have some background in financial engineering. So, so when you look at this book, right, this is some kind of a detour. And when I teach the student to financial engineering, right, teach simulation, and then it's a glass mass book. We talk about how to generate stochastic processes. Start with the Brownian motion, and then OU process, and then CR, and then jump diffusion, which involves Poisson process. So I think this theorem really basically incorporates many very common, interesting models. All right. How much time do I have?
10 minutes.
10 minutes? Okay. That's,
Just a quick question.
Yeah.
For the previous results, when alpha is equal to 0,
Yeah.
you can also characterize how the combined effect of the two things looks like.
What do you mean characterize?
So you said when alpha is
Equals-
equal to 0,
Right.
the two gonna basically both the Poisson part
Right.
and the OU process part.
Right.
And then you can characterize how the two together affect the arrival.
Yeah, well, this is the characterization, right? So this is the scaled arrival process will convert to, when alpha equals 0 will be basically the sum of these two independent parts. Yeah. So, but later when we feed this model to a Q network, to a Q model, these two parts will also take effect in the Q limit. Right. Okay. So, all right. So this is what I emphasized earlier. This was the B tilde actually arises from the conditional Poisson distribution, and in this table you see that this is what I said earlier. So when alpha is positive, then in the limit, the randomness is governed or dominated by the stochastic intensity or stochastic arrival rate. But otherwise, for this part, this is when alpha is 0. But then you can set say for example in the CR model, you set the sigma, the diffusion term to be 0 as well. Then in that case, that CR model will be degenerate essentially to a constant. And in that case, you don't have stochastic arrival rate. You just have a constant arrival rate. So that will actually fall back to the standard Poisson model, Poisson process model. So in that case, the limit will be only this B tilde. But in the middle, when alpha is 0 and when the arrival rate does not degenerate, you have this balanced part, and both the OU process and that B tilde contribute to the limit. Okay. Yeah.
So in the last case, in the Poisson-dominated case,
Right.
You said that you get a constant rate, but isn't there like a transient?
Yeah. When I say constant, I mean so like eventually when t goes to infinity, because so for here, so if you have this guy is 0, so then you have essentially an ODE. So then the xt will be exponential function, decay to 0 exponentially fast. So I'm saying that essentially when t goes to infinity, it looks like a constant at lambda, right? Okay, given that, I mean, I think that theorem is basically the centerpiece. So all the rest Q analysis is quite standard. So that's the whole purpose. We want to build a continuous time model, a continuous time model for arrival process, so that people can take it and feed it to Q models and perform the traditional Q analysis, traditional cafe traffic analysis. So that's why they kind of infinite server approximation or many server Q approximation, QED regime. All these analyses are quite standard, right, given that tractable arrival model. So I'm going to jump directly to, for example, here, if you have an infinite Q system with this new arrival model, then the scaling, of course, you also need to do this sort of a non-standard scaling of the Q length. I'm sorry, not Q length, the number of people in, number of customers in system for this infinite server Q. Then after scaling, you take a limit, then the limit also looks like this. So this is also, you see here, this part, when alpha equals 0, this part actually kicks in. So this is, again, a standard. You would actually expect this part when you perform the same kind of analysis for infinite server Q with the standard Poisson process model. Okay. So yeah, so this is a further illustration. The limit of this scaled number in system Q hat infinite is actually decomposed into these two parts. The first part is come from this stochastic intensity, where the F is the distribution function of the server time. And then you have this part. This part, again, is the standard. If you analyze, for example, MG1Q. Okay. So given this limit, you can, of course, you can derive staffing rules. So this is a quite standard calculation. So for example, you can derive the staffing rules like this, and you have all sorts of explicit calculation, and then the order of the safety level is lambda to the power of this related to alpha. Okay. Here is similar, like compared to before, as long as you have an alpha greater than 1, I'm sorry, alpha, as long as alpha is positive greater than 0, then the safety level is in the order of this term. Okay. However, if alpha is equal 0, then back to the standard square root kind of staffing rule. Okay. Okay. So that was a very explicit calculation related to infinite server Q, but you can actually derive do similar analysis for finite server Qs. So I'm gonna basically the tuition is the same, but here you just you have the same structure in terms of the staffing rules. The only thing that changed here is the leading coefficient beta. We derive a stochastic approximation kind of algorithm to estimate this new beta. Okay, so in last, I'm going to just show you some very simple numerical experiments. So remember that the model that we derive is still a stationary model. So this is kind of like a little bit subtle because the realized arrival rate is a stochastic process, right? So that process obviously is not it is not constant, right? So in that sense, kind of like a time variant, but time variant, I think time variant we really really mean the predictable pattern, time of day pattern. We know that over the noise, over a long time it may have a peak, early morning may have a valley. So that kind of predictive pattern is not the same as the stochastic variation. So that's why our model is still a stationary model. So, but that model can be generalized to capture the time variant pattern very easily. So for example, what we could do is, let me jump back to the model here. So for example, here for the stationary model, we set the long run equilibrium to be constant lambda. So if you want to build in the time variant pattern, you can just change this lambda constant to a deterministic function, say lambda t, you put it here, then that's it, right? So this is something that you can generalize, and that's something that we did in the numerical study. So you have this time variant predictable pattern over the day, and then you plug in this predictable pattern into that CR process, making the long-run equilibrium to be time dependent, and then you can use a new Stein formula and then compare various others. And by the way, the sort of like the objective of the service is the probability of delay, right? You want to keep the probability of delay to be a small number, say 5% or 1%. Given that, you can calculate what is the corresponding stacking level. So here, sort of like suppose your target of probability delay of the system is say 5%. So that's the black dashed line, and then the new formula can match this, can deliver this promised service quality quite well. Okay, so I'm going to stop here, and I think so. The thing that we did is basically we develop a continuous time route process model that is fairly analytical tractable, that can capture this empirical Taylor's law, and then because of this its analytical tractability, you can derive the scaled route process, derive the heavy tracker limit, and then feed that model into a Q network. Q model, and derive the Stein formula. Right. So I'm going to stop here, and thank you.